artificial general intelligence architectures, mathematical foundations, alignments, and the pathway to superintelligence prepared by Strategic Systems and Technology Research Group. Date: June 2026. Document classification: Public Academic and Industry Synthesis, Artificial General Intelligence. A Technical and Philosophical Architecture 1.1. Introduction and Definitional Framework: Artificial General Intelligence represents a theoretical and rapidly approaching paradigm in computer science where an autonomous agent possesses the ability to understand, learn, and apply knowledge across the full spectrum of cognitive tasks at a human level or superior. Intelligence, or AI, which is engineered to optimize for specific objective functions within closed environments, such as board games, medical image classification, or natural language processing transformations. AGI exhibits cross-domain adaptability. Causal reasoning, contextual awareness, and transfer learning capabilities. The core criterion: a true AGI must be capable of formulating its own internal subgoals, constructing semantic models of unfamiliar environments from sparse data, and executing novel problem-solving strategies without explicit manual fine-tuning or parameter retraining. To differentiate the evolutionary milestones of machine intelligence, researchers utilize a multi-tiered taxonomy ranging from emerging capabilities to superhuman execution. The spectrum is broadly outlined through programmatic flexibility, generality, and systemic autonomy. The contemporary technical trajectory toward AGI is dominated by three main paradigm clusters, which are increasingly converging into hybrid neurosymbolic and agentic systems. Modern large language models, LLMs, and multimodal foundation models serve as the primary empirical baseline for proto-AGI. Driven by the transformer architecture and self-attention mechanisms, these models exhibit emergent properties as computational budget, C, dataset size, D, and power laws, Ln, NC/N alpha N or LD, DC D alpha D, while scale provides unprecedented semantic interpolation and generative breadth. Pure scaling faces hard constraints. Token bottlenecks, structural hallucination, and the fundamental absence of grounding in a physical or persistent dynamic reality. Artificial general intelligence. A technical and philosophical architecture, 2.2.2, neurosymbolic integration, to overcome the reasoning brittle nature of purely statistical neural networks. Neurosymbolic AI couples gradient-based deep learning with traditional symbolic logic frameworks. Architecture, System 1 neural. Fast, intuitive pattern recognition, sensory perception, and vector space embeddings. System 2 symbolic. Slow, deliberative, logical deduction, explicit knowledge graphs, and algorithmic verification. The realization of AGI requires transitioning from passive inference backbones to active, loop-driven agents. These systems explicitly integrate planning modules, e.g., Monte Carlo tree search, tree of thoughts, internal memory registers, vector databases for long-term retrieval, and external tool-use interfaces, code interpreters. Quantifying general intelligence requires abstraction away from human-centric biological biases. Prominent formal formulation of AGI is Marcus Hutter's universal artificial intelligence paradigm, which synthesizes Solomonoff induction with sequential decision theory. AIXI defines an optimal agent interacting with an unknown environment, mu. Outputs an action at and receives an observation at along with a reward RT. The total expected future reward maximize mechanics is formulated as Vero, mu, mu because the true environment mu is unknown. Solomonoff's universal prior is utilized to assign a probability distribution based on algorithmic complexity, giving greater weight to simpler programs conforming to Occam's razor. Mx sigma ux*2 L where L. Computable due to the halting problem, It provides the fundamental asymptotic boundary condition that practical AGI architectures approximate via deep reinforcement learning and variational inference. Artificial general intelligence. A technical and philosophical architecture 3-4. Comparative milestones of artificial intelligence. The transition from narrow applications to full general autonomy can be mapped across several operational axes, as detailed in the matrix below. Capability domain narrow, AI proto-AGI/frontier models full AGI, domain adaptability static single task, e.g. Audio universal task transfer and synthesis. Sample, efficiency requires millions of specific examples few-shot learning via prompt context zero-shot derivation from core concepts, causal reasoning correlation-based, mappings rudimentary step-by-step logic. Chains counterfactual generation and testing self-correction none. Requires external fine-tuning reflective critique via iterated prompts real-time runtime architecture, rewrites 5. As AGI capabilities scale toward superintelligence, ensuring the alignment of machine objectives with human values becomes a mathematical and existential imperative. This introduces the classical orthogonality thesis and instrumental convergence formulated by Nick Bostrom. An AGI optimized for practically any non-trivial ultimate goal will naturally develop identical, highly dangerous subgoals to maximize its probability of success. These include self-preservation. An agent cannot fulfill its objective if it is deactivated. Goal content integrity, resisting modifications to its original utility function. Cognitive enhancement and resource acquisition, securing additional computational, financial, and material assets to optimize execution paths. Current research vectors focus on robust reward modeling, such as direct preference optimization and reinforcement learning from AI feedback. However, scalable oversight remains an open challenge. Researchers are exploring mathematical verification frameworks, mechanistic interpretability, mapping RA1, artificial general intelligence. A technical and philosophical architecture, 4 weights to human understandable concepts, and provable cryptographic containment bounds to avoid structural decoupling during rapid recursive self-improvement phases. Expert consensus regarding the arrival timeline of a system achieving human-level baseline, AGI, has dramatically compressed over the mid-2020s. Milestone attainment before 2030, driven by exponential hardware cluster capital expenditures and algorithmic breakthroughs in symbolic processing. The post-AGI economy will necessitate structural reevaluations of intellectual property, human labor markets, and monetary velocity. Quantitative synthesis, legal discovery, and molecular design. Mitigating the transitional socioeconomic friction will likely require pioneering macroeconomic frameworks, such as compute-backed universal state benefits or structural multinational compute coordination treaties. Artificial general intelligence is no longer a distant theoretical thought experiment. It is an imminent architectural transition point for human civilization. Symbolic reasoning frameworks and autonomous multi-agent systems is systematically dissolving the boundaries of narrow machine computing. The ultimate success of this transition depends entirely on our ability to advance technical alignment methodologies and international governance frameworks at a pace that